Welcome to Physics 221, Chapter 17. This chapter is about what's called superposition. That's really interference, how waves interfere with one another. This is an example. This is a soap bubble. You see all these different colors? Those colors are the result of waves interfering, light waves interfering. So here are the objectives. We're going to use the wave model and understand how it differs from the particle model. This is a big deal, how the wave model differs from the particle model. We'll understand and apply the principle of superposition. We'll talk about something called a standing wave. We'll understand that standing waves are the superposition of two traveling waves. We'll study the basic properties of standing waves to death. We'll understand how and why interference occurs in one dimension and also in 2 and 3 dimensions. And then this is just an example. We'll understand beats as the superposition of two waves of unequal frequency. If you're a musician, you already know that. All right, so let's talk about superposition. Again, it's just a fancy word for interference. Okay, so here we have a wave going to the right. We call that a positive amplitude. Here we have a wave moving to the left. We call that a negative amplitude. And you see that right here, this is what it looks like. But afterwards, what happened? This is unchanged. This is unchanged. So what are the waves doing? It looks like they're just passing through each other. Okay, here, positive amplitude, negative amplitude, the amplitudes are the same though, same magnitude. So here it looks like they disappear, but what really happened? They just pass through each other. Now, does that happen with particles? Certainly not. One more example. So positive amplitude, they move through each other. So this is like where they interfere, right? That's where they interfere. And then what happened? This guy just keeps going his merry way, that guy keeps going his merry way. All right, so again, this is where they interfere. This is where they interfere. And that's where they interfere. So waves just pass through each other, as I said, and particles certainly do not. So, once again, we see that particles and waves are completely different, and you want to remember that. All right, now, here's some terms for you. This is called constructive interference. So you can see that they're basically adding, right? Where they interfere, they're adding. So that's like constructive interference, complete adding. Now, if there's complete adding, there's also complete canceling. That's called, oh, here's another constructive. So here, negative amplitudes, and that's where they interfere. So it doesn't matter if it's up or down. So here's destructive. So here's one up and one down. When they interfere, of course, this appears to cancel that. But in reality, they're just passing through each other. So you want to remember those two terms, constructive interference and destructive interference. Okay, now we want to talk about two-dimensional wave interference. Okay, now I have to explain this. So just imagine you have like a little pan, and it's maybe that deep, just covered with water, a little bit of water. Then you have these two, they're called hammers, these two little things that can make waves. So this is one of those things that goes up and down. Here's the other thing that goes up and down. All right, so what do you notice when you look at that? You see bright lines and you see dark lines. And there's a pattern, right? Bright lines, dark lines, bright lines, dark lines. And also the other way, right? So there's a pattern, okay? There's a pattern. So if there's dark lines and bright lines, it means that there's constructive interference as well as destructive interference. Okay, let's analyze this in gory detail. So these are the wave fronts, or the max, the maxes for the waves emanating from A. And the dotted lines are the wave fronts, or the maxes from B. And then you can see that they're interfering. So let's look at where they have X's. All right, here's the max from source A, max from source B, so there's constructive interference. So there's constructive. Okay, here, this is the middle, right? This is between, this is a max from A, that's a max from A. So what's between maxes? A min. So there's a min from A. It's also halfway between the maxes from B, so it's a min from B. So you have a min from A, min from B, you get constructive interference, only it's down. All right, so here's constructive up, here's constructive down. Constructive up, constructive down, and so forth and so on. So everywhere along this line, you have constructive interference. So the water's going really high or really low. Okay, now let's go with the O's. Okay, so here, this is a max from A. But look it's a min from B. So you have a max from A and a min from B. They cancel. So it's destructive interference. Okay, let's look at this one. Okay, it's a min from A, because it's halfway between the maxes. So it's a min from A, max from B, because here's a wavefront. Max from B. So you have min from A, whoosh, max from B, whoosh, they cancel. So everywhere we have these zeros or O's, you have destructive interference. So you have a pattern, right? You have constructive interference, so the water's going like crazy. You have destructive interference where the water's not moving at all. So let's say, okay, here's the pan, right? Let's say it's glass pan, and let's say the pan is right here, and we're kind of, I'm standing here watching it. What am I going to see here? What am I going to see? I'm going to see the water is not moving, sorry, the water is moving here. The water's not moving at all. The water's moving here. Water's not moving at all. So I'm going to see a pattern, right? I'm going to see an interference pattern. That's the important thing, an interference pattern. Now, if we just have one source, right, so this one's not working now, just have one source, I'm not going to see any kind of interference pattern because, you just have one source, so what's it to interfere with? So there's no interference with one source. There's certainly an interference pattern with two sources. So it should be really simple to distinguish between a particle and a wave, right? When waves interfere, they pass through each other, they produce an interference pattern. When particles, well, particles don't interfere, right? They smash and they reflect. They bounce off each other. So particles and waves are completely different. All right. So what I've been showing you are all examples of something called the principle of superposition. So remember, D stands for the displacement. So the net displacement is just the sum of the individual ones. That's all it is, okay? Okay, here's another example. I really like this one. So here you have this, kind of like a triangle, right? Here you have like a half circle, and you can see them moving closer to one another. And here they're interfering, right? So you kind of have this circle triangle thing, and then they just move past each other, right? They just go through each other. So it looks like nothing happened to it. And again, that's how waves act. All right, two identical pulses of opposite amplitude travel along a stretched string and interfere destructively. All right, so in other words, you have one like this, moving like that, then you have one like that, oops, whatever, like that, moving like that. Okay, so they're going to interfere destructively. Which of the following is or are true? So pause your video and figure it out. Okay, let's answer it. Two answers that are correct. All right, so if they're going to if they're going to interfere destructively, there's going to be a place where the string is completely straight. And I showed you some pictures of that already. Now, all right, so that means that there's a point of the string that does not move up or down, and I showed you that earlier. Now, number two, it's important to realize that. This is false. So number two says, when the two pulses interfere, the energy of the pulses is momentarily zero. Well, how can that be? I mean, energy is conserved, right? This guy has energy, it takes energy to move. This guy has energy, it takes energy to move. The energy doesn't go away, because energy is conserved, like we learned in Physics 121. All right. Okay, now I want to do a demo, and I don't know if it's going to work, but we'll do our best. Oh, boy. If we turn the light off and I shine the light, think we'll be able to see it? Okay, let's try it. So what I'm going to do is I'm going to shine a laser pointer through two, so So this is a piece of glass, and it has slits in it. And I have two narrow slits that are super close to one another. So what I'm going to do is I'm going to shine the light through those slits. But I got to find it first. Oh, there it is. It was too dark. All right. I'm going to shine it. There. See that? Okay, let's turn the lights back on. Okay, so let me explain what I just did. So let's say that this was metal, real thick metal. Here's a slit, here's a slit. Here's a screen. Here's a light, a laser pointer or whatever. Okay, there's two options. Light is made out of particles or made out of waves. If light's made out of particles, the particles act like bullets. So, you see light going every which way, but it's going to be stopped by the metal, but yet some are going to go through this slit. Some are going to go through this slit. So all we would see on the screen is a bright spot here and a bright spot here. On the other hand, if light is made out of waves, then we're going to see basically what I showed you earlier. This. We're going to see this. We're going to see an interference pattern on the screen. And I hope you were able to see that. When I did my little demo, we did not see two bright spots. We saw a bunch of bright spots. We saw an interference pattern. So what does that imply? It implies that light acts like a wave. Okay? Light acts like a wave. All right. Now we're going to learn about something called a standing wave. And remember, there are two kinds of waves that we're going to talk about. We're going to talk about transverse waves and longitudinal waves. So first we'll talk about the easy situation, and that's standing waves on a string. So it's transverse waves. So this is hope it works. So if we were in the regular classroom, we would do a demonstration, which takes a lot of equipment to set up, but we're not going to do that, sorry. We're going to see a YouTube video. Now the sound's not going to be any good right now, whatever.
What we have here is a frequency generator. It's connected to what's called a wave driver. It's just a speaker. It's going to pump up and down at whatever frequency I set this guy to. When this guy pumps up and down, well, he sends a wave. Sends a wave down to this end, the wave reflects, comes back. Now, if I set it to just any old frequency, let me just turn this on. Well, let's go. So it's sending waves back and forth, but these waves are out of sync, if you like. They're not exhibiting consistently constructive or destructive interference at any one point. But if I set it here, for example, I have what's called a standing wave. That is, the wave that's sent down and reflects constructively interferes with the next wave that comes down right at this point. Now the waves that come down and reflect destructively interfere with the incoming waves right here. And that's called a node. I can touch it and it still is working. So the node is not moving. Here it's moving up and down, and here it's moving up and down. And we'll see that in a second with the high-speed camera. So here we have what's called the second harmonic. It's the second possibility for a standing wave for a string that's held at both ends. Because notice, this is a node, and the middle's a node. We have three nodes for this wave. Now, like I said, second harmonic. Well, what's the first one? The first one will be half this number, so 8.5. And there we go.
That's a high-speed camera.
It's basically the scenario of a jumper. Now, I can find any of the other, all of the other harmonics are multiples of this number. So we just saw that 2 times this number was the second harmonic, or the second possibility. Well, if I go 3 times this number, I should get the third harmonic. Well, 3 times 8.5, I guess that was that around 25.5. And there we go. So that's the third harmonic. How many wavelengths is this? Well, it's 1 and a half. 1 and 1/2 wavelengths. And it's easier to see in high speed. So check out this shot with the high speed camera and verify for yourself that it is 1 and 1/2 wavelengths. So again, third harmonic, 1 1/2 wavelengths. Well, let's go to the sixth harmonic. The sixth harmonic will just be double this frequency. So we go up to 50. And there we go. That's the sixth harmonic. Beautiful. And it's 6 times the fundamental frequency, which we measured in the beginning to be 8.5 hertz. So check this guy out. We have 1, 2, 3 wavelengths. And in the next video, the explanation video, we'll go through the calculations and the derivations.
All right. We're going to actually do that now, so you don't have to watch the next video. So what do you notice? So as the narrator indicated, you start out by sending a transverse wave this way, and then it reflected back this way. And at certain frequencies, we produce those standing waves. Standing waves. All right, so we're going to talk about these standing waves in gory detail. We're going to analyze them mathematically, and oh boy, a lot of work. All right, so here's what it looks like. So this is what it looks like at certain frequencies. At certain frequencies. So at certain frequencies, no oscillation ever. Right? No oscillations, no oscillations. But here it goes, it goes, it goes from 0 to the max and back, right? Right? So it's not always up there. It goes, whatever. Okay? All right. So, and again, you only got this pattern, this standing wave pattern at certain frequencies. All right? So, we're studying interference, so that means that we have to be able to explain this, right? We have to use the laws of physics to explain this. So that's what we're going to do now. So we're going to do some math. All right. Okay. So what did the guy say? He said initially there's a wave, let's say going to the right, and then it reflects, so it goes to the left. So what are we doing? We're adding 2 waves, right, or the displacements. So this is displacement to the right plus displacement to the left. Now we already learned this in the previous chapter. So the displacement of the wave moving to the right, A sine kx minus omega t. To the left, A sine kx plus omega t. And again, we're saying that it's the same wave, right? It's just reflecting. So they have the same amplitude, same wave number, same frequency, same everything, except one's moving to the right, one's moving to the left. Now, we have to figure that out. Now, you remember in high school when you took your trig class and your teachers made you memorize those addition and subtraction formulas and you thought it was a complete waste of time? Well, guess what? We're going to use them now. All right, so here we go. So this is what you probably forgot by now. So these are the things that you learned in high school. So sine alpha minus beta, sine alpha cos beta minus cos alpha sine beta. Then for the plus, it's sine cosine plus cosine. All right, so those are just things you learned in when you took your trig class. Now, what we have, so this is like your alpha, this is like the beta, right? So what we have is we have a sine alpha minus beta plus a sine alpha plus beta. Okay? So you just, we're going to have this added to this. Piece of cake. All right, so, well here, this just adds, so you get 2 sine alpha cos beta. This cancels, right? Because here's a minus sign, here's a plus sign. So this added to this gives you 2 sine alpha cos beta. Make sure you understand that. Go through it, right? So what I'm saying is, so this should just be 2a sine kx cos omega t, just by using those addition and subtraction formulas. So we just use these formulas from trig, and this is what we get. We get 2a sine kx cosine omega t. Ta-da! All right, so using these things, these wonderful formulas from high school, we get this. Now, this just depends on x, right? Right? I mean, this is cosine omega t, right? But this just depends on x. We can just call that an amplitude of x. All right, so that's what you do. That's what you get. Everything's wonderful. Now, here's the question. Is this a traveling wave? So that's a question from the previous chapter. Remember what we learned last chapter. If it's a traveling wave, it has to be a function of kx minus omega t. Well, is that a function of kx minus omega t? No, it is certainly not. So this is not a traveling wave. And no kidding, right? When you saw that standing wave pattern, it didn't look like anything was going back and forth, right? Okay. So it's not a standing wave. I mean, sorry. It's not a traveling wave. It's a standing wave. Okay, so let's talk about this here. All right, so what does this mean? So this part, which is like the amplitude, but it depends on x, right? Depends on x. This is the shape of the string, the amplitude at some x. That's what it is. And here, at each x, what does the wave do? Right? So pick an x. At any x, what does the wave do? Well, it oscillates up and down because it's a cosine, right? It oscillates up and down. Okay? So there you go. All right, now what we want to do is explain the observations, right? That's the job of a physicist, right? So here we go. Let's see. Oh, hold on. Not yet. Oh, and again, I forgot to show you something. So here, the amplitude is 2a, right? Because the max and min sign is plus or minus 1, so the amplitude of this is 2a. So go from 0 to 2a, 0 minus 2a. Okay, whatever. When time equals 0, cosine of 0 is 1, right? So this would be 1 at time equals 0. So the outer curve is the amplitude function a of x. That's what I just said a minute ago. And the oscillation amplitude changes with position. Okay, whatever. Right? This changes with position. Okay. Just repeating myself, sorry. All right, now let's start talking about the observations. So first let's discuss this. Here, here, and here. So for all time and eternity, there's never going to be any oscillation at those points. By the way, we're going to explain these points, and then everything in between. And you should follow this closely because you'll have to do this in a lab and perhaps on an exam. So you have to understand it, not memorize it. Okay, so what we want to do is we want to find the locations where the amplitude is always 0. So so you look at this formula, and we want the amplitude to be 0 for all time and eternity. So therefore, which factor has to be 0? This factor or that factor? Remember, we want it to be 0 for all time and eternity. Well, I think you have to agree it's this factor, right? because this is going to be between 1 and minus 1. So this factor has to be 0 all the time at these specific locations, which we're going to now find. All right, so we want 2a sine kx to be 0. And we're going to find, like I said, find the positions. Well, who cares about the 2a, right? So what we really want is we want sine kx to be 0 for all time and eternity. By the way, that's called a boundary condition. You'll learn that in math if you haven't already pretty soon. Boundary condition. All right, so again, what we want to do is figure out what values of x this is always going to be true for all time. So here we go. All right, so when is sine of anything equal to 0? Well, 0, pi, 2 pi, 3 pi, right? 0, 180, 360, and on and on and on. But we like pi's because we're doing radians. All right, so if this is true, this kx has to be 0, okay, but where else? Like I said, pi, 2 pi, and on and on and on, right? All right, okay, so that's fine. But again, we want to find x, so we got to divide everything by k, all right? Now what's k? Remember, k is 2 pi over lambda. But we want to divide by k. Well, that's the same thing as multiplying by 1 over k. So 1 over k is lambda over 2 pi, right? So we want to multiply everything here by lambda over 2 pi. All right? So multiply everything by lambda over 2 pi. So it's going to be 0 still. Okay, this is going to be lambda over 2. Okay, this is going to be just lambda, and so forth. All right, now let's write it just a little bit differently, and you'll see why. All right, let's write this as 0 lambda over 2, 2 lambda over 2. And guess what the next one would be? It'd be, well, let's just do it. Okay, let's just do it. Let's put 3 pi, okay, 3 pi, and then this, what would this one be? This would be 3 lambda over 2, right? So this is going to be 3 lambda over 2. So you see a pattern, right? You see a pattern. So, I don't want to keep writing this. It's too much trouble. So we're going to say, therefore, x equals m times lambda over 2. Well, what's m? It's not mass. It's an index, okay? It's an index. So m is 0, 1, 2, 3, blah, 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 blah. All right? So this is just a shortcut way of writing this, right? If m is 0, we get 0. If m is 1, we get 1 times lambda over 2. If m is 2, we get 2 times lambda over 2. M is 3, we get 3 lambda over 2. So this is just a nice, convenient way of writing it. All right? Okay, so these are the positions where there's no oscillation. Now, there's a name. If you paid attention to that video, the guy used the name. It's called a node. And it's simple to remember this. The first 2 letters are N-O, right? Node. No oscillation, all right? So node is no oscillation. So in other words, there's no oscillation at 0. There's no oscillation at lambda over 2. There's no oscillation at lambda, and so forth and so on. So we just did it, okay? We did it. So what did we just find? We found the locations where we found where the nodes are located, all right? That's it. So that's where the nodes are located. So make sure you can do that on your own. Okay, now what we want to do is we want to find the we want to find the positions of where there's maximum amplitude. Okay, maximum amplitude. Now, come on, we already know it. If this is a node, that's a node, that's a node. Where's this? It's halfway between the nodes, right? So, okay, all I'm saying is we know the answer. But we want to do it mathematically because you're going to need to do this in your homework, in your lab, and in the test. So let's do it. It's very similar to what we just did. Okay. So now we want to find the positions, again, where this is a max. Now, what's the biggest sign? 1, right? Sign goes between 1 and minus 1. So therefore, if this is going to be the max, we want sine kx to be the max, to be 1. All right, so that's all we want. So we want sine, can you see the green? Okay, so we want sine, we actually want 1 and minus 1, right? We want 1 and minus 1. So we want sine kx to be plus or minus 1. And again, that's a boundary condition. All right. So we're going to do the same as before. Okay, so where is sine equal to 1? Well, 90, 270, and on, all right? Pi over 2, 3 pi over 2, and just keep going, all right. Okay. So, therefore, we want kx to be 90, pi over 2, and 270, 3 pi over 2, and so forth and so on. All right, just like we did before, remember, so k is 2 pi over lambda, therefore 1 over k is lambda over 2 pi. So we're going to multiply everything here by 1 over k because we want to get x by itself. So therefore we do that, we get x. Okay, here it's going to be pi over 4, right? Pi over 4. Here we're going to divide by the 2 pi. It's going to be 3 pi over 4, and on and on and on. Okay? So how are we going to write that in a real cool way? So here's how we're going to write that. We're going to say m plus a half times lambda over 2, where m is 0, 1, 2, on and on and on. Okay, let's see if it works. Put in 0. 0 plus a half is a half. Half times lambda over 2 is lambda over 4. What? Oh, I goofed up. Sorry. Sorry. Okay. All right, so that works. Put in 1. 1 plus a half is 3 halves. 3 halves times lambda over 2 is 3/4 lambda. So we got it. All right? So this now is the condition for the maxes. And again, we knew it, right? Because this was 0. This was lambda over 2. This has to be lambda over 4. This was lambda over 2. This was lambda. This has to be 3/4 lambda. So, I mean, lambda over 4, 3/4 lambda, so forth and so on. Okay, now, if these things are called nodes, what do you suppose these things are called? So think of the Book of Mormon, the converted Lamanites. What do they call themselves? Anti-Nephi Lehis, right? So what are we going to call these things? Anti-nodes. Oh, brother. That's supposed to be a plus or minus. I don't know what happened there, but anyway, whatever. Okay, so anti-nodes. Okay? And let's see. That's a good place to stop.